Welcome, Physical Science 20. This is 16.4, Calculating Enthalpy Change. We're going to do most of this booklet together, but I'm also going to leave you with some questions to do as well, because it can be kind of tricky. So first of all, look at the first question here. We'll do this one together. Explain what are some limitations of using a calorimeter to determine the enthalpy or heat or energy for a chemical reaction. And the main thing there is that we obviously can't do every single reaction in the lab or try to duplicate it. So they may be too difficult to do. They also may be too dangerous to do. So there has to be another way of determining how much heat is involved in a reaction without actually physically doing the experiment. And that kind of leads to something referred to as Hess's law. So there's a lot here to squeeze into this part. So, and it states if you can add two or more thermochemical equations to produce a final equation for a reaction, then the sum of enthalpy changes for individual reactions is the enthalpy change of the overall. So in other words, if we can manipulate equations to represent an overall equation, all we need to do is just simply add up those heats involved with each one, and we can get the total. And this next example, I'm going to go through that and illustrate how. So for the next one here, now this is pulled from the textbook or the handouts that you have. And basically the question is this. What is the enthalpy change in this reaction? 2S plus 3O2 yielding 2SO3 gas. When given these two equations. Okay, so you're given these two equations. We know the enthalpy for these equations. How can we manipulate these equations to result in this? If we can do that, then the resulting enthalpy will be equal to the overall enthalpy as stated in Hess's law. So the Hess's law is kind of, it seems kind of difficult, but once you see how we work the example, it'll make sense. We'll go back to it, read it again, and see how that all fits in. So first of all, what we have to do is look at manipulating the equations to make it look like this equation. So first of all, I'm going to look for sulfur, S. And if I look in the other equations here, I will see that I have sulfur in this first equation, isolated. Now, sulfur in this first equation is on the left-hand side of the arrow. It's a reactant. Here it's a reactant as well, so that's good. But over here, I need two of them, and I only have one. So what I'm going to have to do here is, with this first equation, multiply by 2. If I multiply the S by 2, I'll have to multiply everything by 2, basically doubling everything in this equation, and I'll have 2 moles of sulfur on the left. Moving along here, oxygen, I'm going to skip. Always skip oxygen because most equations have oxygen in them, so it'll be a little bit too difficult to try to manipulate things if oxygen is in most equations. So next, I'll look at SO3. And SO3 is in the second equation, it's right there. The only problem is I need it to be on the product side and it's on the reactant side. I need 2 moles of it. I've got 2 moles of it. So the only thing I need to do here is reverse the equation. If I reverse it, make reactants products and products reactants, it'll be on the appropriate side that I need it to be on. So applying those two operations will lead me with the following. So I'll have, so my first equation multiplied by 2, so I'll have 2S plus 2O2 yielding 2SO2. And my enthalpy, I also have to double that. So I'll get negative 588 kilojoules. Okay. I'm just going to move this viewer over here because I see that I'm off. There we go. And the second equation, reverse it. So what was a product? I'll try to line up the arrows here. It's usually a good idea to do that. 2SO2 gas. Oops, I'm also going to have to fit the oxygen in there. 2SO2 plus O2 yields 2SO3. And I think, yes, I'm supposed to have gas there originally. And what happens with enthalpy, what was an endothermic becomes an exothermic when you reverse it. Okay, so that's what we end up with. And the key thing now is to look at, are there any things that I can cancel out? And if we look close enough here, in this first step we get 2 SO2 formed, and then 2 SO2 is used up in the next equation. So you can think of it being produced and then used up. So we can cross that off. And what we're left with is this. We're left with 2S plus, and over here I have 2O2, 1O2. Together that makes 3O2. And over on the right hand side, 2SO3 gas. So what Hess's law says is that if I can manipulate equations and get the overall equation by combining two equations, combining the leftover enthalpies will leave me with the enthalpy of the overall reaction as well. So when I do that, I get negative 786 kilojoules. So if you look here carefully enough, the original equation, 2S plus 3O2 yields 2SO3. I got it. 2S plus 3O2 yields 2SO3. And then combining the overall enthalpies gives me the enthalpy of the equation. So that is basically what you do with Hess's law of summation. I think, let's see here, I have time here. I'll maybe go over to the next part here, the next question that I have. And basically it's kind of a visual illustrating what could this actually look like. So here, if you just draw this little graph here, I'm going to try to fit this all in. So dotted line there. We have our two. So originally in our first equation that we manipulated, 2S plus 2O2. And if we look there, my smartboard's a little slow here. What we did here is we had 2S combined with 2O2 yielding 2SO2, and it involves the release of 588. So I'm going to draw that, hopefully. So when we formed our 2SO3 gas, that involved the release, losing energy, because we don't need it, of negative 588 kilojoules. And then in the second step, we had that 2SO2 combining with the last oxygen to yield 2SO3 and the release of 198 kilojoules. So I'm just going to rewrite that here. We took that actually that was SO2. That 2SO2 combined with an oxygen to yield, there's where the SO3 is, 2SO3. I'll draw an energy level about right there. And that involved the release of 198. Or we usually show that as negative 198, meaning that it's being released. Negative 198. So overall what happened here, you can see that the delta H in total was negative 786 kilojoules. So it's kind of a visual display illustrating what those two equations did. When we manipulated it, the first equation produced 2SO2, involved the release of negative 588. Then that 2SO2 combined with the last oxygen, which involved the release of negative 198. So in total, from start to finish, negative 786, which illustrates exactly what happened earlier on over here with the two equations. Okay, what I'll have you do while waiting to watch part 2 of the video is try this question here. So number 4 illustrates, do 2 practice problems that are in the handout, number 20 and 29. So here's 28, and you may have to write really, really tiny or use another piece of paper to get these all in here. You may just fit 28 in this space and use a piece of loose leaf for 29, but I'll show you this for a while so you can copy it down. See if you can try that. How do you manipulate the green equations to get the blue? So you may want to pause the video right now And then coming back, number 29, you may want to pause it now so you can get number 29 and work on them while you're waiting for the second installment of this video to be online. Thank you.